yeah, so yeah, the talk today that I give would be about some topic of Fermi realization of deconfined quantum critical points. Yeah, so it basically some kind of designer Hamiltonian on the lattice that are realized by the fermions, such that we were able to do some exact quantum Monte Carlo simulation. Yeah, well, of course, nowadays after the effort of so many friends from the bootstrap community, we sort of know that at 2+1D, these kind of deconfined critical points are probably not really a real critical point, but sort of like a pseudo critical phenomenon. But it's still interesting to see that we can do some lattice simulations. So it basically contains two parts. So one is the quantum phase transition between dynamic generated quantum spin Hall phase and a superconducting state. Another one is a realization of a 2+1D nonlinear sigma model with west to minus Witten's term based on Landau level projection. Yeah, so many of our setup are based on the picture of Dirac fermions on in the condensed matter community. So we are somehow sort of interested in systems from graphene-like system. As you know, this is like the band structure of graphene. And if you are interested in the low energy physics around half field case, then we know that they are Dirac cones. And when you study some like solid state stuff, and we know that you could have even some interesting phenomena, even if there's no fermion correlation. As basically, in some sense, we can have like a topological insulator. So in this toy model, that's actually a quantum spin Hall state that, because of some spin optical coupling term that explicitly breaks the spin symmetry, and when this kind of term exists, actually we can get out the bulk of the two-dimensional space. But because there is non-trivial topology, we know that there can still be helical edge states that propagates along the edge of the two-dimensional system. And we are somehow more interested in the correlated electron behavior. And then, so we try to think of the phenomenon that what could happen if we can sort of like dynamically generate a quantum spin Hall phase. So that idea is to think that to take those spin current operators that can S O3 order parameter that can fluctuate in space. And if we couple it to some three-component vector field in the space, and then try to think what is the picture behind. So basically, then you know oh, sorry, this is not yet dynamical in this picture. So this is purely static. So I use this as an introduction. But then in the next step, so I will go to the dynamical part. Yeah. So I mean, in this part, there's if we treat this as a classical variable, then there's not yet any dynamics. But then, if we want to add some dynamic fluctuation of this three-component vector field, then there are multiple ways. So the way that we come up with is to just introduce fermion four-operator interaction that is writing this way. So as you can see, we actually really have perfect square of those spin current operators in space, and we have a summation of all the three polymatrices here, and then this is a Fermion interacting term that actually doesn't explicitly break any symmetry of the Hamiltonian. So yeah, this is an interacting system that respects all the spin rotational or lattice symmetry. And then we could think that if you introduce like Hubbard-Strasnovich decomposition of this kind of Fermi interaction, then that's sort of like the picture that we talked before. But then in this picture here, the O3, all the parameter field really have a dynamical fluctuation. So I mean, then what is a meaning of a quantum spin Hall insulating state in this sense? I mean, if the fermions in the bulk are gapped because of the long range coherence of this O3 order parameter field. I mean, in the sense that if you can still see long range or finite correlation even at very far away limit, then that basically means that you have a spontaneous broken of this spin rotational symmetry, and then that means that we have a spin Hall insulator that is dynamically generated. Yeah, so I mean, then this is sort of like this is the part of the numerical calculation. This axis is really the interacting strength that we talked before. So because it's when there's no interaction, this is a Dirac semi-metal that has vanishing density of states at low energy. Then we know that it should be stable if the interacting strength is very weak. But then what we found by numerical calculation is that if you increase the interacting strength strong enough, then we do see that there is a phase transition between this semi-magnetic state to a dynamically generated quantum spin Hall phase. So as we introduced before, so we identify this symmetry broken state just by measuring the long range or the long range correlation of this O3 order parameter based on this kind of correlation ratio. So this is sort of like being the accumulate in the sense that it is dimensionless quantity. But if this scales up to 1, if we increase system size, it means that there's a symmetry broken. But if it decays towards 0, it means that there's no long range order. I mean, this guy itself is a renormalization group invariant in the sense that if we see that there is a crossing, that means that there is a critical point here. Yeah, so I mean, yeah. Sorry. Yes. Yeah, I will introduce more about this. Yeah. You mean why is this? Yeah. I will talk more about this. Yeah. So yeah, so this as you said, this is a growth new O3 critical point. So of course, this is nothing to do with deconfined critical point, or not directly related, but it's also something interesting that we want to comment on. So I mean, this is we think that this is basically a growth new Heisenberg phase transition that is same as the one that happens between like Dirac semi-metal and anti-ferromagnetic insulating state, in the sense that the Dirac fermions are gapped because of the spontaneous symmetry broken. Right? So I mean, this is nothing but like a field theory of a Dirac, free Dirac path plus a O3 order parameter that is Yukawa coupled to by the fermions, and so there's actually no real difference between this quantum spin Hall masses and the antiferromagnetic masses. I mean, the only difference is like there's a sign, and so in this picture there's a sign change if you go from one Dirac cone to another cone, right? But from the criticality point of view, there will be no difference. Sorry, which Z2 symmetry are you? Yeah, so yeah, yeah, so the difference between this gamma 0, gamma 3, gamma 5 and this guy is that for this mass you switch the sign when you go from one Dirac cone to another. But I think if you just want to study the criticality, so probably not like about the nature of topology and so on. So I guess you can just do a link the two guy by like a unitary transformation in the four flavor space, right? Yeah. You sorry, which order parameter? Yeah. This is the order parameter. Exactly. Yes. Yeah, as intrinsic, he's puzzled about the the difference between this guy and this guy. Yeah. Okay. Maybe we can talk about this later. But yeah. Yeah. You mean there's an additional Z2 symmetry that might be different? Okay. Yeah. Now I'm a bit nervous, but yeah. Yeah. There's a bit, yeah, at least so this guy also breaks the time reversal symmetry, right? But this guy doesn't break time reversal. Yeah, but yeah. Sorry, you mean this M? That's actually 8 if you also include the real spin. So we have spin and AB sublattice of honeycomb lattice, and also the 2 cones degrees of freedom. So that's totally 8 components. That's why. So basically, this polymatrix here, this is spin up and down, right? So, but this has 4 forming components. Yeah. I mean, and anyways, we really did some a lot of systematic extrapolation of the universal class at this critical point, and indeed, what we compared with many other numerical works, and also some perturbative renormalization group approach, is that we really compared this phase transition to those happens between Dirac semi-metal and the antiferromagnetic ordered phases. At least we didn't really find a obvious mismatch between the exponents and those other semi-metal to AFM transitions. But I mean, there's always a question on the precision, right? But yeah. So yeah, that's another. So then now the question is that about this quantum spin Hall phases that is dynamic generated. So why this is also interesting? The low energy excitations of this so correlated insulator. So they are not only Gauss-Slow modes, but also they are also they are like skyrmion configurations of this O3 vector field, right? So we know that when these vector fields are completely polarized, then we do have a particle hole symmetry. But then if you have a sort of like skyrmion configurations of this O3 compact O3 order parameter field, then we know that it's the skyrmion configuration of this quantum spin Hall carries electron charge too. So this is not particle hole symmetric anymore. Right? So this picture has been understood like a long time ago by Abanov and Wickman, like 20 years ago. So yeah, so then this somehow also like inspires us that if you can have a way to condense like the creation or annihilation operator of these skyrmions, that basically means that we could have a way to condense pairs of electrons. That's in the next step we wanted to, or it inspires us to think about the possibility of some other symmetry broken state. That's basically SV superconducting state here. And so what is pretty amazing for us is that if we increase the interacting strength again, then we found actually if the interacting is strong enough, then the quantum spin Hall long range order this actually vanishes. And at the same point, we found that there is actually another. So there is actually the S-wave superconducting state that develops at the same point. I mean, this is nothing but the correlation ratio of the Cooper pairs. You can really see that it increases if we increase system size here. So, I mean, okay, then there's a phase transition here, but so the first thing is that this is well, not really at least in the bulk, this is not a fermionic phase transition, because if you look at the fermions one particle excitation gap, this is always open at across this phase transition. There's no gap closing. And another thing is that at least within the numerical calculation of our finite societies, we didn't found any evidence of like first order phase transition. So then at least this we sort of believe that this is like a deconfined critical point. Yeah, so I mean then so actually, yeah, at a lattice point of view, there's always many ways to do some fine tuning, but at least if lambda is very big, this is nothing very fancy or surprise. We can even do a mean field analysis, just decouple those four fermion interaction terms. and you can really see that there are terms that correspond to the coupling of Cooper pairs between those different size, and at least this superconducting states in large interaction is perfectly fits in the mean field picture. Yeah, so I mean, but we sort of think that the continuum field theory, okay, at this deconfined critical point is should be somehow same as the one that happens at like for example the GQ model at two-dimensional quantum spin system that has been introduced a lot last week by Professor Sandvik. Right? So basically the continuous description, we thought that it should be like free Dirac part plus 5 components. So basically 3 plus 2 equals 5. These two are just the U1 or the parameter fields of the superconducting part. Right? If there is always a finite amplitude of these 5 components, or the parameter field, then at least the Fermions single particle gap are always open. But then if you integrate out the gapped fermions, and then we know that this should be nothing but like nonlinear sigma model with West minus geometrical terms here. That's basically, so the case thing is that the mass terms of these 3 and the 2 guys, they anti-commute with each other. Right? So, and of course there has to be many other symmetry broken terms, like this kind of intrinsic anisotropic terms that tunes the symmetry broken, and also some other symmetry broken terms based on lattice regularization. Right? So, but then because we expect that this is nothing but the same phase transition that happens on like GQ model at 2-dimension or 3-dimensional classical loop models, and then we tried to extrapolate the universal class of this phase transition. And indeed, if you look at the correlation length exponents or the anomalous dimension, we found that these are basically the same universal classes, at least within our finite system sizes. Yeah, so yeah, there are some slides of basically of the numerical approaches, but I guess if you are not so interested in the details of Fermi and Monte Carlo, so maybe we can sort of like skip this page. So the key thing is that we try to come up with a way to do a path integral, in the sense that you can do a Haber-Strasnovich decombination of those Fermion four-body interactions, and then so each of the auxiliary fields are actually associated with a real and positive boson weight if there is sort of like asymmetry. But the thing that I want to emphasize now is that this is not so cheap, right? So if we so for fermionic Monte Carlo in the determinant approach, so that basically so the numerical efficiency of this kind of calculation really skews although it skews polynomially as a function of the volume of the system, but it skews as volume to the cube. So this is really because of the of the Fermion statistics that we are doing. So this is much more expensive than like quantum Monte Carlo calculations or like quantum spin models that was introduced last week by Anders Sandvik, right? That actually goes much quicker, and they can really get much larger system size. Then if we are not that efficient, then why is it still or interesting for us to do this kind of calculation? So at least I think there's one thing that could be funny. That's because I think because we really use fermions to realize this problem, and then so there's a difference in terms of symmetry. So I think so in the quantum spin model approaches at 2D, we know that so the thing that is important for the transition is that the lattice rotation is not a continuous symmetry, right? It's actually a discrete symmetry, so it's only invariant if you do a 90-degree rotation. But in the continuum field theory, so it's sort of expected that you need this guy or this symmetry break term to be irrelevant when you approach the critical point. But in the fermion counterpart, so I mean this phase transition to the superconductivity. So what matters, or what matters, is not the lattice rotation, but actually the U1 charge conservation of the fermion. That's actually not that's always an exact symmetry that is not broken by the lattice Hamiltonian. So it's in this sense, it's sort of like we get rid of one dangerous irrelevant symmetry broken field on the lattice point of view. So if you remember, so yeah, there are several symmetry broken perturbations in the action. So this kind of guy actually breaks down the U1 symmetry, breaks U1 symmetry down to Z4. But we don't have this term. So in this lattice model simulation, yeah, I think we do have some like numerical way to identify this kind of stuff. So for example, we can calculate the uniform susceptibilities of the conserved quantities, like the spin. So in a work by Professor Sandvik, so several years ago, so they really argue that because there are two divergent long scales, because of that dangerous irrelevant Z4 symmetry broken field, so this uniform spin susceptibility, it has sort of like a very non-trivial scaling behavior, finite size scaling. That is because you have two correlation length exponent. But at least in our numerical approaches, I mean, we didn't do finite size scaling, but instead we did the temperature scaling. But then what we found is that at least within our finite size calculations, we didn't find any evidence that there are two divergent long scale. So really the susceptibility of the conserved quantities at the critical point, they decay linearly as a function of temperature. This you mean this G? Yeah. No. This is not all the parameters, but this is actually the generator of all the parameters. Yeah, which part? SO3 part or the U1? Yeah, we calculated both. So the one is for the SO3 part, one is for the U1 part. Yeah, but on the GQ model, of course, the U1 part is sort of like not very nice. We don't know how to define that, but so they only calculate the SO3 part. Yeah, so I mean, that is so in the next step we are also interested in. So we sort of at least have a feeling that if we would do some lattice regularization based on fermions, then we could sort of like study this kind of interesting field theory without so many dangerous symmetry broken terms. In the next step, so we are thinking that can we find some way to study a nonlinear sigma model with exact O5 symmetry, in the sense that some other higher order corrections that break some symmetry are also not exist in our lattice regularization. So that's what we studied is here is based on some projection of fermions to the Dirac Landau levels. Yeah, so this is sort of like a bit similar to what Yin-Chen talked last week, but this is not did on a sphere, but we did it simply on a two-dimensional torus. So I mean, this is beautiful picture here is nothing but Hofstadter butterfly. So this is the picture that you can generate if you put like a lattice. So in this case, it's a honeycomb lattice in an orbital magnetic field. Then there are sort of like interplay between the lattice constant and the magnetic length scale. But then what the physics that we care about is just the low energy physics around the Dirac cones in the wake in the small magnetic field region. So then we play the trick that we, in the sense that we projected 4 flavors of fermions to this Dirac Landau level here, and so of course the system that we worked on are not not really based on the Hofstadter butterfly on the lattice, but actually Dirac Landau levels in the continuous space. And we don't have any lattice in our model setup, and this is basically the designed Hamiltonian that we played with. So these are the fermion four operator interactions based on the perfect squares of those fermion bilinears. So these are basically the different 4x4 trace matrices that correspond to different mass terms. For example, 3-component AFM or VBS guys. So I mean, if you have if we tune the coupling constant in front to be identical, yeah, to each other, then you know that there's an explicit O5 symmetry, that in the sense that you can rotate between all the 5-component vector fields here. So yeah, so it is actually a picture that is proposed by Subir Sachdev several years ago, in the sense that they can also explicitly derive this nonlinear sigma model with a west to middle Witten sum at 2+1D. So because it's also similar physical picture, because the fermions are single fermions are gaps because of the finite amplitude of this O5 component field, and then you can do like gradient expansion to integrate out the fermions. Right. So and then this is the numerical part that we are playing with. So we only care about the physics at the half field case of those Landau levels. And because of the particle hole symmetry, there is actually also no sign problem for this fermionic calculation. So that's the first thing that we benchmarked is the uniform is the charge susceptibility at low temperature. So you can see that there's an exponential decay of this of the charge susceptibility. That means that the charge fluctuation are killed, and then there's is a perfect insulator at low energy, and that's so at least the necessary step to say that we could have a sigma model. Right. So, and another thing that we want to mention is that there's almost no tuning parameter in this designer system, because we sort of locked our model Hamiltonian to be exactly O5 symmetric, right? Then there's sort of like no tuning parameter. But then there's only one parameter that we can play with. That's actually SU4 symmetric density interaction here that doesn't break any symmetry. So this one is not related to any symmetry. It's still O5 symmetric, but if we play with the ratios between this SU4 density interaction and the others, and there is sort of like a way for us to fine-tune the 1/G. I don't know how does the field theory friends call it. I somehow call it stiffness, but maybe this is not a very precise name. Right? Something called this coupling constant. So yeah, this is a continuous parameter that we can so for like play with. We can shift this guy continuously. And yeah, so then so what we can do numerically is then also the correlation functions of the O5 order parameter. So we can also define things like a correlation ratio that is based on the 5 component order parameter fields, and then study if you have a stable power law state phase or not. I mean, as a function of this kind of this coupling strength in the field theory. So what is not very surprise is that if this coupling is strong, or if the order O5 vector fields are stiff, then we indeed found that there is always a O5 so spontaneous symmetry broken if we go to large system sizes. I mean, the correlation ratio, it first decays a bit, but then finally it still goes up. That means that we have a symmetry broken. But what is sort of interesting is that if the 1/G is not that big, then within our finite system sizes, we found that there is a stable power law state or critical phase. I mean, of course, we cannot know finally if there's always a symmetry broken if we approach to the thermodynamic limit, but at least this is what we can do, at least within finite numerical calculation. You mean what does it mean? Yes. Yeah, this guy. This is basically, this phi dagger phi coupled to the identity matrix, right? So this one doesn't change any symmetry. It only changes some, 1/G, this kind of constant. Yeah. So yeah, so at least so we can sort of like do a time problem-free calculation of this continuous field theory. And yeah, when this coupling strength is not that big, at least there should be maybe a finite but a very large length scale that we cannot see within our finite numerical calculation, right? At least below these correlation lines, it always seems to be critical. I mean, then at least there are, before you do the like the numerical calculation, there might be several scenarios. For example, 05 symmetry broken fixed point and a disordered fixed point here, or a critical point in the small coupling constant regime, or there's always a symmetry broken regime, no matter how you tune the 1 over G. But at least, so numerically, we sort of think that there is a stable power law phase at weak coupling regime. But I guess, but I think nowadays, so with the help of the bootstrap community, we sort of like know that there is it should be somehow always a weakly first order phase transition, right? It's just how weak it is, or how small the
Sensitive are you to there being another relevant operator very close to market? That would be another possibility. Not guaranteed that it's weakly first order, it could be second order, but there could be another operator very close to marginality.
Yeah, then so which kind of relevant operators?
Relevant single. So like instead of having to tune one parameter to get to a fixed point, maybe you have to tune two parameters, or maybe the second parameter you're tuning corresponds to an operator close to marginality, which is why you're not so sensitive.
You mean it's a relevant operator, but it's also a singlet, like 05 singlet.
Yes.
Yeah, I'm not sure about.
I'm just saying because like the bootstrap results you're talking about, they just say that you can't have a theory that has no S5.
Yeah.
Like, well, what did you do about it? I'm just wondering how sensitive you guys would be to seeing that if it was close to market.
Yeah, I'm. But then if it's a two-dimensional quantum Hamiltonian, then are you saying that if we can add like another perturbation that doesn't break any symmetry to see? Yeah, this is the thing that yeah, this is the thing that I don't know. Yeah, so that's basically the mainly the two parts of of this work. So at least we sort of interesting to see that the DQCP based on lattice regularization of fermions, so we can do it with less symmetry broken, and then at least we can sort of like see the pseudo criticality within some finite size calculation. Yeah, that's the main part of talk. Yeah, thank you.
Any questions?
So in your simulations, do you say any signatures of critical point? Let's say I'm talking about the RG flow diagram that in the box, right? If that's the RG flow, then there will be a critical point between this SO5 safety and SO5 symmetry breaking fixed point, right? The green fixed point you draw.
Yeah, you mean this one, right?
Yeah. So do you see any like signatures in your data of this green fixed point?
Yeah, so I mean that's what we actually showed. So basically, because this is defined to be like a renormalization group invariant quantity.
Yeah.
Then that basically means that if we extrapolate, if we scale up to larger and larger volume, if this guy sort of like keeps the constant, this sort of like means that we have a parallel decay of the correlation.
Yeah,
And
you see the middle one.
yeah,
One-
that, yeah,
you see
yeah,
two
can,
phase. One phase would be the conformal phase, typically. The other phase would be SO5 simply breaking.
yeah, and in between you can have a critical point. Right.
yeah, that's sort of like another like a multi-critical point, right?
Yeah, you can call it multi-critical, but in your setup, it's a critical point if you keep the SO5 symmetry.
Yeah, that's right. So that's the thing that we cannot distinguish. So if this is really the thing in the thermodynamic limit, that would mean that finally if we can go to, I mean, huge system types, that basically means that if this in this regime, finally at the large size limit, so this guy always scales up to 1. But in when we are in the left hand side of the green point of this critical point, it's always saturates to a finite constant. It means that this is always a parallel, right? But then, I mean,
In between, you will have a new universal.
separate, yeah, but that's something that we cannot at least identify.
I see,
Yeah.
okay, thanks.
Okay, how does this story fit in what Chong was explaining? He was using some duality web, start from some duality, you do some S or T transformation, you arrive in a fermionic theory. He did it for the easy-plane GQ model, but your fermionic formulation of DQCP, does it manifest in this duality web story? Or, I mean, like you start from which seed duality and you do some operation, you get this duality. Yeah.
I mean, yeah, I guess if you want to really identify the duality, exactly, so we should really, you know, because, you know, this is not really related to duality, right? So this is not even a
No, I'm talking about the fermionic formulation of the DQCP you proposed. That should be due to the CPN model, but this duality is it somewhere in the duality web or?
Yeah, this I don't know. Yeah.
Okay.
Yeah.
Just give some quick remark. So first of all, the model he simulated is not a continuous field theory, right? It's a non-randomizable, strongly interacting model. And the one interesting aspect of that model is that you have exact SO5 or O5 symmetry. And indeed, you can write down a continuum field theory that is a QCD3 series with 2 Dirac fermions coupled with SU2 gauge field. And that field theory has exact SO5 symmetry. And it's one of the duality web dual theory of the SO5 DQCP. And I think it's, at least to me, it's very natural to expect that this type of nonlinear cell model will describe those gauge series, QCD gauge series.
Try.
Any further questions? Okay, well, in that case, let's thank the speaker.